备好了，那我们或许可以稍微往早一点。各队都准备好。好，那我们就先请3队简单自我介绍一下。reporter team 开始。
Good afternoon, everyone. We are Team E1, and I'm 庄立奇、赖新宇、许少恒、罗恒立 and 张义婷. Thank you.
谢谢。And the opponent team.
Team 2 I'm 杨佑一、陈佑琪、陈宣慈、侯文清、陈千惠。
谢谢。
I'm the captain from Team Excelsior, and I'm Chen Yuqian. She is Lin Yichen. He is Zheng Yuchen. He is Li Haiwen. He is Hong Zhang. Thank you.
谢谢。然后您注意简单自我介绍一下。从我开始，我是台湾师范大学张国哲。
林中兴 from Hong University 东海大学。
黄明轩3月
李沃龙从台湾师范大学。
中华物理系叶望系。谢谢。Okay, let's start the debate. So, opponent, please pose the problem.
We would like to strategy number 11.
Number 11. Pumping stroke.
We accept the challenge.
Okay. So it's problem 11, pumping stroke. Yeah, and the players for each team, please write down your name. Lisa, please start your presentation.
Good afternoon, fellow contestants and worthy judges. We are from B1, and today we are going to introduce problem 11, straw. So first, let's start with the problem statement. A simple water pump can be made using a straw shaped into a triangle and cut open at the vertices. When such a triangle is partially immersed with water with one of its vertices rotated around its vertical axis, water may flow up through the straw. And we're going to investigate how the geometry and other parameters affect the pumping speed. So first, I would like to introduce the phenomenon. So basically, water spills out of the vertex opening of this triangle right here when the straw undergoes the spinning motion. So this is, so they basically right here, and they went up like this. And this is our force diagram. Fc refers to the pseudo-centrifugal force, or you can also call it a centrifugal force, and Fg refers to the gravitational force, P refers to the pressure due to Bernoulli's principle, and the N is the normal force, and pressure loss is the pressure loss during the motion because of the friction between the fluid and the wall of the straw. So we're going to explore into three parameters in our experiments. The first one is the length of the straws. The second is the caliber of the straws, or you can also call it the thickness of the straws. And the third one is the vertex angle of the straws. And we would like to define right here that the pumping speed in our experiment refers to the volume of water pumped per unit of time, or you can also call it the flow rate. And in our theory, we support our theory with Reynolds transport equation. So it is, allow me to explain a little bit. The first one is the combination of forces, and the second chunk refers to the rate change of the volume, which in this experiment, since the volume of straw is static, is 0 because there is no change. And the third one is the mass flow rate momentum, right here. And CV refers to control value, CS refers to control system, V is velocity, and the capital V is the volume, and A refers to area. And we're going to include some of the forces into this formula. The first one is the pseudocentrifugal force, or the centrifugal force, which is exemplified right here. Which is shown right here. And the second one is the gravitational force, which is demonstrated right here. And then I'd like to explain a little bit with the pressure loss. So the pressure loss is caused by the friction, and you can use the Darcy-Weisbach equation, which is right here, to demonstrate it. And after you use the Darcy-Weisbach equation, you will get the equation like this, And you can see there's a friction factor right here. And the way to determine this friction factor depends on whether a system is turbulent or it's laminar. And to determine whether a system is turbulent or laminar, you gotta calculate the Reynolds number. So the way to calculate Reynolds number is right here. And since Reynolds, in our experiment, all the systems Reynolds numbers spans from 8,000 to 12,000 after the calculation, which is higher than 4,000, which means that they're all turbulent. And if they are turbulent, the way to determine the basic friction factor, we have to inspect the Moody chart. And the y-axis of the Moody chart is the relative pipe roughness. And so this is our Moody chart. Well, the brightness of the image is pretty weird. But as we can see, the Reynolds number spans from 8,000 to 12,000, and is the x-axis. So the x-axis is right here. It's about 10 to the fourth power, and it's right here. And also the roughness of PVC, or the material for straw, is approximately 0.0015. And if we divide it with the diameter of our straw, the thick straw will be right here, and the thin straw will be right here. And as what I said, there are going to be two basic friction factor because, as I mentioned previously in our report, we are going to test it with different thick straw, with the straws with different thickness. And then there's also the influence from the Bernoulli principle, and so we list the Bernoulli equation right here. And after that, we plug all the previous formulas back to the original Reynolds transport equation, which is like this. And then we expand it, we get this. So the velocity is like this. And to know the flow rate, we have to multiply the velocity with the area and the density. And next. So I would like to introduce our experiment setup. The first one is the empty fish tank to collect the water. The second one is to drill with the angular velocity of 105 radians per second, or 1,000 revolution per minute. And this is a beaker, 1 liter beaker with 1 liter of water. And all these three pictures are the pumps, the straw pumps that we're going to test in our experiments. And the next one is the volumetric flask to determine the accurate volume, and the dropper, and also the graduated cylinder. So, yeah. So in our experiments, we're going to explore how 3 parameters affect pumping speed. So there are different lengths of our straws, including 4, 5, and 6 centimeters. And the calibers, there are 2 different calibers. The first one is the 6 millimeter caliber, and the second one is the 11 millimeter straws, caliber straws. And the third one is the vertex angle, including 30 degrees, 60 degrees, and 90 degrees. So experiment 1, we're going to know how the correlation between the length and the pumping speed goes. And in our results, we found out that with longer straw on each side, the pumping speed of the straw diminishes, which is different from our common sense, because longer straws often correlate to higher velocity, technically. However, the reason we discover is that the longer straws experience greater loss from friction, because they're longer. They have more influence from friction, and therefore leads to the decrease of velocity and flow rate as a whole. So this is our diagram. So you can see as the straw length increases, the flow rate decreases. And the light color is the theoretical value, and the dark color is our experiments. And there's some deviation from our theoretical value and our experimental value, which we will explore later. And also, there, according to the so the explanation for it is the Darcy-Weisbach equation. So as the R, or you can call it the length of the straw increases, then the pressure loss will also increases. And next, we would like to talk about the caliber of the straws. So with higher cross-sectional area, more water is pumped out of the straw. So this statement means that thicker straw has a higher flow rate, and as you can see right here. So this is the 6 millimeter straw, and this is the 11 millimeter straws. And yeah, the 11 millimeter straws is obviously, the flow rate is obviously higher than the 6 millimeter straw. And to get into the reason of this, yes, of course the cross-sectional area of the straw increases along with the flow rate of water. So we can see the flow rate equation of our straw, and there's a variable A right here. So A actually means the cross-sectional area. And number 3, the vertex angle of the straws. So with lower vertex angle, more water is pumped out of the straw. So this is the 30 degrees straw, 60 degrees, and 90 degrees. And there are still some deviations from the theory and the experiment, but we will explain it later. So, and in the end, we discovered that with lower angle, the contingent value will increase. So right here, you can see with lower angle, the influence from Bernoulli principle will appear, and therefore affecting the overall results. And there are some of the boundary conditions that I would like to mention. To understand the boundary condition, we have to set several variables. So we set the length of the straw to 5 centimeters and 60 degrees vertex angle. And we want to know the vertex angle, the boundary condition for our angular velocity. And after our meticulous calculation, the result is about 11.66 radians per second. So drill with a spinning speed of lower than this value, and with this setup will not activate a pumping motion. And also we would like to understand boundary condition for the length of our straws, and therefore we set the variables of angular velocity to 105 radians per second, and also angle to 60 degrees, the vertex angle to 60 degrees, and conduct the meticulous calculation. And later we found out that the boundary condition for the length of the straws under this setup is approximately 11.1 centimeter, which means that the straws with the side length above this value will not activate a pumping motion. And there are some points for future research, which I believe is the reason for deviation from the theoretical value and the experimental value. So the first one is the influence from air pressure. The air pressure is also something that will be affected because of Bernoulli principle. However, due to the difficulty in quantifying the air pressure, we do not consider it in our experiments. And we also believe that this is not a big influence, but I believe this is something for future research. There's also some influence from the depth. And the depth that the straw dipped into the water can also affect the potential pumping speed. And also the Coriolis force exerted on water can also be a potential reason that affects the pumping motion. So in conclusion, with longer straw we have lower pumping speed. Thicker, we have higher pumping speed. And with lower vertex angle, we will increase the pumping speed. And the boundary conditions was mentioned by before. The angular velocity below 11.66 radians per second, and also the straw length longer than 11.1 centimeter. Thank you.
You have questions from the audience?
Can you turn to page the serial introduction? There's a chart. Yeah, this one. Can you explain this one? What?
Okay, so I believe when we were putting this on PPT, there's certain brightness problem with the image, so I'm going to explain this. So the x-axis refers to the Reynolds number, and which spans from 8,000 to 12,000. So we just, because there's not a big difference, we just use the value 10 to the 4th power.
And what's this one mean? This one?
You mean this one?
Yeah.
The x-axis is the Reynolds number.
Okay, and
the y-axis, can we go back to previous page, is the relative pipe roughness, or also epsilon divided by the diameter.
okay. And can you tell me how many percent your error bar?
How many percent?
Your data chart.
Right, data.
Yeah.
Our error bar is determined by the uncertainty A, B, and 3. Uncertainty type A, B, and C.
Okay, I see.
Yeah. So if you divide the standard deviation. Okay.
And how many times do you do the experiment?
The experiment?
Yeah.
For each one I do 5 times.
Okay, and take the average for the data?
No. So you gotta have a standard deviation, and we divide it by the 5. So the trial number, the square root of the trial number. This is the A-type deviation.
Okay, 6.
Okay, Chen, please.
Okay, we are team 2. I'm opponent. And I want to say the reporter's pros and cons. Reporter's pros is he express well and understand the statement well. That's really match the picture. And cons lack of experiment data because I don't see the form or something about the data. And he doesn't produce of experiments. And our overview is that first is the desert, the series, and it's like this. And this one is Warab, and the length of stroke, the caliber of stroke, and vertex angle. And experiment, I will ask him for that. And conclusion is high cross-section error, low water compound, and lower vertex angle. Future experiment, air pressure and depth and this like this. And I think this one is well because he think about the carbon statement well. And improvement, I will ask him the question next, and the first one is how to measure the water that in the straw. And since I will discussion with the reporter.
Okay, so I noticed that you have a lot of questions about the experiment setup and how I conduct the experiment. So may I use the board so I can explain?
Okay.
Okay. So about the experiment setup, I have so first we have a fish tank because we don't want water to get anywhere. So we have a beaker in the middle, and the beaker is filled with 1,000 milliliters of water. And after that, we will attach our straw pump to a drill. And the drill, then we dip the straw pump to the water surface, and we specifically want the straw pump to dip under the surface for 8 millimeters.
This one is all 8 millimeter.
Yeah, because we want to control it. We want to control it. Use this piece. Yeah. So we will ask a operator to operate a drill and an observer to observe the motion, because we want the relative distance between this straw pump and the water to be 8 millimeters. Because if we use the straw pump for long enough.
Sorry, did you consider the water in this straw?
When doing what?
When doing your experiments, did you consider the water in this straw? And it won't go here.
I might need further information about this.
Sorry, you said?
I might need further information about your question.
Okay.
Under what condition should I consider the water inside the straw?
Is this small can to be ignore?
You mean a mass?
Yeah. The amount in the straw's water can be.
Well, I believe that your question is about should we consider the mass of water inside the straw to be a influencing factor for the spinning speed of the drill. Is that the question that you're asking? Okay. So we believe that the mass of water inside the straw has very little difference from each other when undergoing a spinning motion. We actually tested it. It's all about 105 radians per second or 1,000 revolution per minute.
So you didn't consider it because it's too small.
Yeah, and we recorded a video to test the drilling speed, and it's all the same.
And it's all the same in this one.
With very little deviations, about positive or negative 5 spin.
So it doesn't affect your experiment data.
Barely.
No.
Yeah.
Okay.
So if you want further information about my experiment setup, I can also explain it. So when
Sorry, can you tell me how to control this S millimeter? Because you put it in the water and it will spin.
yeah, so this is a detail, right? So we actually colored the 8 millimeters part right here with black paint. And when conducting this motion, we asked an operator to operate the drill. And while operating, because we don't want his hand to slip, so we asked another observer to observe his motion. And to make sure nothing goes wrong.
So if you use hand to take it or use it on something, you can take this one. You use hand or you use tools.
Okay, so here's the problem with the tools. If you undergo the pumping motion for long enough time, the water level actually drops. The water level, and as the water level drops, you always want to maintain the relative distance between the straw pump and the water to be 8 millimeter. So your hands have to move. However, the tools cannot do the same thing.
So you use hand, but you didn't consider your hand shape or well.
So regarding this this question, I already answered. We will ask another observer to observe the motion and make sure nothing goes wrong. And in fact, because even after we ask an observer, there's still going to be a possibility to go wrong, right?
Yeah.
So we actually did a short experiment, or you can also put a preliminary experiment. So when it's about 8 millimeters, we test whether when it's about 8 millimeters and 16 millimeters. If your straw pump when under the surface about this range, the difference of 8 millimeters and 16 millimeters will not have a large difference.
So you don't consider this error, yeah? You didn't consider this one error.
Well, like I said before, we did a preliminary experiment, and it proves that whether the straw pump go under the water surface for 8 millimeters and 16 millimeters does not have a big difference, and that's why exactly the reason why I put the depth of the pumping straw as our future research topic.
So you do some experiment to prove that this one and this one
Will not have a big difference, yeah.
Yeah, so its error has so small it can be ignored.
Basically, in our experiment, yes, but it also, I believe that also contributes to the reason why there's a little deviation from our theoretical value and our experimental value.
Okay. This one I see, and this one I want to ask the results think your series and formula.
Our theories and formula, in which aspect?
And the series is not. I think your series is not all connect with your experiment because your experiment one.
Experiment 1,
Yeah.
and we go to experiment 1. So, yeah.
Yes, the series and this series is your own series and the formula is your take, but how do you consider these two? Sorry. How do you connect these two together?
How do I connect the theory?
This is all your subject opinion, and this is all your opinion. So
Well, no, because our theory is supported by the Reynolds transport equation, which is kind of a foundation theory for fluid mechanics.
sorry, can you show me the series and
the first
I
page.
think this is all your take to prove your data, but I think this is all your opinion. It is not object.
Okay, so you mean this? It's the pressure loss, right?
Yeah.
So what is the first? The first variable in that equation, Reynolds transport theory, is the combination of forces. So I would answer that the pressure affects the forces. P multiplied by A equals the forces.
Your formula, can you show me your formula?
The first page of the theory. Yeah, this one. So yeah, the sigma F with the vector sign on it refers to the combination of forces.
And so you said you take this one to prove your experiment, but did you consider another thing to affect your experiment?
Well,
another things like another force, not just this one.
yeah, this is why I put so many potential factors in our future research topics, because these forces that we listed are the most obvious ones, and there are a lot that are not quantifiable and probably have very little influence, but still have an influence on the experiment, and that's why I put them on future research topics.
Okay, so you say that sigma F, and there are a lot of F. So can you explain which F will affect that?
Can we go back to the fourth diagram, the phenomenon line? Yeah, this. So basically, the combination of forces in our theory, we only consider this direction because all the other are cancel out, and so C is the pseudo-centripetal force or the centrifugal force.
Oh, sorry. Do you consider the pumping the straw is not all the same material? It's inside is air. So you couldn't put the center of mass like here.
Oh, so in this case, we are so during the pumping motion. So for most of the time, water fills the entire straw during most of the pumping motion, and that's exactly where our pumping motion starts, right? Because water pumps out. Water has to fill the entire straw to get pumped out of the straw.
Okay, and what this angle will be considered with your straw angle?
Yeah, as shown in our formulas, I believe we already stated that FC will be FC sine theta and FG will be FG cosine theta.
Okay, and can you turn to the experiment 3?
Experiment 3?
Yeah. I want to ask the relation between angle and your this force, this one, and yeah.
I'm sorry, I might miss further.
And can you turn to the force?
The fourth diagram.
Sorry, the time is up.
Thanks.
Chen Youqi, please summarize the discussion.
Okay. The first one, I asked the setup of the experiments, and he showed me this one, and he said a lot of things can small to be ignored. So just like this and this one, and he set observer here. So I think this is a good way, but it is not the best way because the observer will have some mistake, and it is human made. And the next one, I asked the series link the formula, and he showed me a lot of things, but I only think it is all his opinion. It's not object. And the third, I asked some question about the angle and the force. this is my summary. Thanks.
Yeah.
Sorry, question for our reporter. How do you measure the pumping speed?
How do I measure the pumping speed? Well, so it is through our pumping speed. We like our experiment. We stick a straw pump into the water and then we start to drill, and the water will get pumped.
I talk about pumping speed, like the μL minus divide second or something else.
Well, like I said, we wait the water to pump out of the straw pump, and then we measure the amount being pumped out, and we divide it by time.
Thank you. So, question for both. How will the immersion depth affect the phenomenon? Immersion depth. Since you just use your hand to hold the straw, so when the straw is down more into the water, so how will it affect the phenomenon?
Oh well, like I said, within small range, it's not going to affect very much.
I don't agree with him because I think that small it will a little affect, and from this picture we will see that some water will put into the first the disc container. So yeah.
I agree with the opponent said that it will change, but I disagree with your points because I think the immersion depth will affect the velocity of the water, so it will affect the pumping rate. Thank you. So the question next for the both: do you think there will be a boundary condition of the length of the straw? Why or why not?
The density of the straw.
Boundary condition of the length of the straw.
Yes, there will be.
But how
No, sorry, I don't understand what you mean.
the boundary condition of the length of the straw? Will there be a boundary condition of the length?
Yeah, I think this is right. I think
Okay,
this
but
is right.
as you just mentioned, the centrifugal force equation. So when the R increase, which means the length of the straw increase, so the rotating radius will increase. So according to the force equals to R omega ping pong, R omega squared. So how will, if you increase the rotating radius, how will it affect?
If I increase the rotating radius, it also means that we're going to increase the length of the straw, right?
Yes.
So how would that affect what?
Affect the phenomenon. Like you say that the length of a straw won't have the boundary condition, will have the boundary condition, but when the radius of rotation increase, the centrifugal force will also increase, so they won't make the boundary condition, right?
Yes, I agree with you that that's
Okay,
going to have a
thank you.
better condition.
So the time is up.
Thank you. Problem 11, pumping straw. The problem statement said that a triangle-shaped straw can be a water pump which is rotated around its vertices axis. So the water may flow up, and we will need to investigate how the geometry and other relevant parameters will affect the pumping speed. And I'll mainly focus on how is the water pumped out by the straw, and how different parameters will affect the phenomenon. For the review of the report, he demonstrated the phenomenon which was the water pumped out by the straw, and he used Reynolds transport equation, Darcy-Weisbach equation, and the Moody charts as his theory. And he has three different parameters in the experiment part, which are the length of the straw, vortex angle of the straw, and the caliber of the straw. He considered different theory and have clear illustration. However, he didn't explain the deviations and didn't demonstrate the phenomenon well. And also, he didn't use a stable experiment setup. And the review of the opposition, she noticed the lack of control in the experiments, and noticed the lack of deviations and analysis in the experiments. She also discussed about the geometry of the straw. However, she has unclear feedback of the report, and didn't discuss the energy dissipation, and also the boundary condition. For our questions, we asked for how do you measure the pumping speed. The reporter answers that we calculate the volume of the pumping out per time, which was same as our experiment. And for our question 2, the immersion depth. I asked for how will the immersion depth affect the phenomenon, and the reporter answered for it will have minor effect on the phenomenon. And the opponent said that it won't change. It will change. And I think the immersion depth will affect the velocity of the water, so that will affect the phenomenon significantly. For the point mix, they didn't discuss the parameters about the immersion depth and the angular velocity. When the immersion depth will affect the water velocity, and the angular velocity will increase the pumping rate. And they didn't discuss the definition of vertex angle. And also, they didn't control the reporter's lack of control for the angular velocity. And they also didn't discuss the experiment deviations, which I think may be because of the vortex or the perturbation of the water. Thank you.
Thank you. Okay, and concluding remarks.
Well, I believe the opponent and the reviewer have contributed a great deal to this discussion, so I would like to appreciate that. But there are several points that I would like to reiterate or explain. So first, the reviewer asked us whether we have considered the boundary condition, and yes, we did. And they also raised a question about the gravity center, but as we explained previously, in our condition, in the theory, water already filled out the entire straw. So the condition that the part of the air is still in the straw is basically not existent. And they also have some question regarding our experimental setup and experiment procedure and the immersion depth problem. Well, I do agree with the reviewer that it's going to influence, but what I meant is that in such a small range, which is 8mm to 16mm, it's not going to have a big effect. And we also, and the opponent also claimed that our theory is objective. However, however, we proved our theory with our experiments. And also the question about angular velocity is being raised. But like I previously mentioned, we actually recorded several videos to test the angular velocity of the drill. And it shows that they're basically the same because they have very similar loading. And this goes the end of my presentation. Thank you, everybody.
Thank you for your presentations. Questions from the group? the straw, there is still a pressure difference between the top and the bottom of the straw. When you immerse the straw inside the water, there is a pressure delta P.
Yes.
So far everything is static.
Yes.
But now when you start to rotate the triangle, because you have all those formulas, could you tell me how would the angular velocity change delta P? And then when the angular velocity is 0, you already have a delta P. And when they start to rotate, can we see from some of the equations how the angular velocity change? Because delta P is not enough to give you injecting water. The water comes out of the straw not because of this delta P.
Yes. Well, this is considered as a minor factor because, as stated in our experiment, the centrifugal force also has its influence.
So this is the second term is what is the second term?
It's density and the velocity.
Yeah, if you only have 0, then you only have the second term.
Yeah.
What is the second? What does the second term come from?
I'll give you the second term right here. The second term is the height. Density multiplied by gravity multiplied by height. So our tangent is the height.
Any comments? About the effect of the angular velocity on delta P.
Because of the angular velocity will produce the centrifugal force, and if we need to pump out the water, we need to have the centrifugal force which was larger than the gravitational force. So if we didn't rotate it, it can't overcome the gravitational force. So the water may not pump out by the straw. Thank you.
Yeah, so I agree with her. Well, actually, in our equation, we include the influence from the centrifugal force.
Okay, I also would agree with the reviewer.
Okay, thank you. Scores for the reporter here. R 6, 8. Score for the reporter are 6, 8, 5, 6, 5. The scores for the reporter. 5, 5, 4, 5, 4. Okay. Let's take a break here.
他中间看手机，空更多。
Yeah, the break is 10 to 15 minutes.
完整，我觉得 review 可能会有意义，可能就是
summarize 那边我们要讲什么？会讲 discussion 的内容吗？因为刚刚有一个，刚刚跑出来的时候，不要再讲 discussion 的内容了，我觉得。
他说10到15分。
他刚刚说10分钟吗？
他刚说10到15。看一下。
好吧。
回去吗？回不去。
公司店里的，我打扮2队。
继续加油，好吗？不行，那就好，我们自己定时间，然后看看。 他讲。
等他们回来，人差不多出来。
最高境界，就是跟当兵一样。班长都不认识你，最高境界。对。对啊，最高境界。
我听过了，
黑道对。
很少听到好，那个时间差不多了哈，那我看我们就开始 second stage。Okay, so the opponent please propose a problem.
We would like to challenge problem 14 relation. Thank you.
Okay. Problem 14.
We accept.
Oh, good. Okay, so it's problem 14. Ruler trick. Reviewer, please write down the name. Teacher, please start your presentation.
Good afternoon. I'm from Team Typt and I'm Typt, and we're going to talk about number 14, ruler trick. So here's our problem statement. We place a ruler on the edge of the table and we drop the ball at its free end. Then the ruler will fall off. But if you cover it with a paper, then the ruler won't fall off. So we're going to explain this phenomenon and investigate the relevant parameters. And our main focus would be finding the relation between factors and the angular acceleration that makes the ruler fall off. And so here's our outline. So we're going to introduce our experimental setup and then talk about our theory, then our factors, and then our experiments. So here's our experimental setup. So this ruler is the ruler that we do the experiment, and this is the paper that we cover with. And this ruler is for us to check that the height of the ball dropping. And we tie a heavy thing at the ends of the string to make sure that our ball can drop at the same space on the ruler. And so this is our experimental video. So from the video you can see that the ruler didn't fall off because there's covered with a paper. And first we want to know if it was influenced by the weight. So we do the same experiment with the flattened paper here and also the crumpled paper. So we crumple it and put it. So they are the same weight, but they are in a different area. And from the experiment, we can see that the flattened paper can resist more force. So we can tell that weight isn't the primary factors that influence our experiment. So we're using atmospheric pressure, so the ruler can resist more force. And here's our theory. So when the ball hits the ruler, then it gives a force to the ruler and makes a torque. And so do the paper. The air pressure present on it. So it also gives a torque to the ruler. And so the total torque of the ruler would be the torque of the ball minus the torque of the paper. And from the parallel axis theorem, we can tell that the moment of inertia equals to this. And M stands for the mass of the ruler, and L stands for the length of the ruler. And this R stands for the fulcrum to the mass of the center to the ruler. And so we know that torque equals to angular acceleration times the moment of inertia. And so we get this. And so the angular acceleration equals to this. And so from our theory, we can see that when the mass of the ball and the velocity of the ball is bigger, then the acceleration will be bigger. Then the ruler will fall off more easily. But when the mass of the ruler and the fulcrum to the mass of the center of the ruler is bigger, the acceleration will be lower. And so when the area of the paper and arm of the force of the paper is bigger, then the angular acceleration is lower, then it won't fall off that easily. So here's our factors. We are going to change the different direct deflections of rulers, and we change the type of covering, and we change the length of the suspended part of our ruler, and also we change the height of the ball when it falls, and also the area of the coverage and the direction of the covering. So here's our first experiment. So we change the rulers with different deflection, which also means we change the different types of rulers. So we do this experiment with a 30 centimeters non-flexible plastic ruler and also the flexible one. So we are going to move the ruler's free end further away from the table's edge or the closer to the table's edge and test if we drop the ball from 50 centimeters, it will fall off or not. So we have to tell that here we said the direction of covering is vertically. The vertically in my experiment we mean like this, and this is what horizontally mean in our experiment. And so here's our data. We can see that when it is the suspended part of the ruler is 10 centimeters, the ruler that is this non-flexible plastic ruler, it already falls down, but the 30 centimeter flexible plastic ruler still stays on the table. So we can see that flexible plastic ruler can resist more force. But we think that might be because when an external force is applied, the flexible ruler, it would deform rather than fall off. So, but we can't control how much it deforms. So that might lead to inaccurate results. So we will use non-flexible plastic ruler in the further experiments. And the next is changing the types of covering. So we changed the covering with A4 paper or the L-shaped plastic folder. So we also moved the ruler's free end closer or further away from the table's edge and test if the ruler will fall off or not. So here's our data. And we can see that when the suspended part of the ruler is 10 centimeters, the ruler that covered with A4 paper already fall off. But the ruler that covered with L-shaped folder, it didn't fall off. So we can see that covering the ruler with the L-shaped folder provides significant assistance in resisting the force. So we think that might be because the static electricity between the L-shaped folder, which is made of plastic, and the surface of the table. So there is static electricity between them. And also, the weight of the L-shaped folder is a bit heavier than the A4 paper. But we can control the static electricity of the L-shaped folder. So we will use A4 paper in further experiments. And the third one is we change the direction of our covering. So we change the direction of our covering with vertically or the horizontally. And we also move the free ends of the ruler and closer or further away from the edge of the table and test if it will fall out. So again, this is vertically and this is horizontally. And here's our data. We can see that when the suspended part of the ruler is 13 centimeters, the ruler that covered with A4 paper placed vertically didn't fall off, but the ruler that covered with A4 paper and placed horizontally already fall off over 10 centimeters. So conclusion is, when the paper is placed vertically, then it can cover much further to the fulcrum of our ruler. So the arm of the force is longer. So which also match our theory. When the arm of the force of paper is bigger, then the angular acceleration will be lower. Then the ruler won't fall off that easily. And the next experiment would be the area of coverage. So we change the covering with A4 paper or half of the A4 paper. And so this is A4 paper and this is how we cut it off. And this is our data. So when the suspended part of the ruler is 8 centimeters, the ruler that covered with the A4 paper, half of the A4 paper and placed vertically already fall off. But the A4 paper that placed vertically didn't fall off. And then we do it with horizontally one. So when the suspended part of the ruler is over 5 centimeters, the ruler that covered with half of the A4 paper placed horizontally already fall off. But the A4 paper that placed horizontally, that ruler didn't fall off until 10 centimeters. So we can see that no matter which direction, in vertically or horizontally, the paper is, when the ruler is covered by paper in a larger area, it can resist more force, which also matches our theory. The area of the paper is bigger, then the angular acceleration would be lower. So the next experiment would be changing the height of the ball when it falls. So we change the tennis ball height from 25 centimeters to 50 centimeters every 5 centimeters. And so we also do this experiment. And here's our data. So we can see that when the height of the ball is bigger, then the ruler will fall out. So we can see that when the height of the ball is bigger, then the velocity of the ball is bigger. So, which also match our theory. When the velocity of the ball is bigger, then the angular acceleration is bigger. And thanks for your listening.
Thank you. Questions from the court?
So I would like to ask a few questions. So, let me make sure you are analyzing the critical conditions, right?
Yeah.
Okay. Did you match your experimental data with your theory?
Yeah.
Okay. How do you define the width and the length of your paper, or you just consider the area of the paper?
Oh, I just consider the area.
Okay.
So I always use the A4 paper.
Okay. Did you measure or calculate the force acting on the ruler?
Yeah. The torque.
Yeah, I mean, you measured.
Yeah, I did some calculation.
No, I mean, did you measure the force, or you just it's in theory?
In theory.
Okay. Is there a limit of what your theory can explain?
I don't think so.
Okay. Did you find the boundary limits in your experiments?
Yeah.
Okay.
But when we change different factors, the boundary changes.
Okay, thank you. How do you define the deflection of ruler?
So deflection, it is pretty complex, but it is.
Can you please change to the page where we have the deflection of ruler? Okay, can you just give me a short answer of what is the deflection of ruler?
So it is influenced by the material of the ruler and also the length of.
Okay, thank you.
deflection 是哪一个？就是尺受到外力的时候，它会是这样算不出来。
你看上去之后就会这样，就是这样子。
honorable juries and fellow competitors. I'm the opponent from Team Excelsior, and I'm going to oppose problem number 14, ruler trick. So this is the problem statement. Place a ruler on the edge of a table and throw a ball at its free end. The ruler will fall. However, you cover a part of the ruler with a piece of paper and repeat the throw. Then the ruler will remain on the table while the ball will bounce off it. Explain this phenomenon and investigate the relevant parameters. So I'll be mainly focusing on why the ruler remains still on the table and the critical conditions of this phenomenon, and also the air pressure of the paper. And this is the outline of the report. So first she talked about atmospheric pressure as her main force acting on the paper, and also the torque and the parallel axis theory. And for her experiments, she tested a ruler with different deflection, which I'll talk about later, and also the type of covering, and also the direction of covering, and the area of coverage, and also the release height of the ball. And these are her strong and weak points. So first, she had a lot of parameters discussed in the report, and also she had a clear model of the experimental setup, and also she considered about boundary conditions. However, she didn't explain that the direction of the airflow during the impact, and also the lack of experimental chart of the data, and no theory line. And she didn't mention how they measure the elasticity of the ruler, and she didn't explain. And also she didn't have explanation of deviations in her experiments. So these are the points I want to discuss. So the first will be atmospheric pressure, and also the boundary conditions of this phenomenon, and also the material difference, which are elasticity and also the material of the paper. And for the theory part, I'd like to talk about energy dissipation during the phenomenon, and also for the atmosphere, which are the pressure difference, the direction of airflow, and also the velocity of airflow. And also the acting force on the ruler, and the ball's contact time with the ruler. And for the experiment part, I would like to talk about how the paper size affect the result, not just for the area, which are the width and the length of the paper. And also the colliding position of the ball, which might affect the torque and also the pressure that gives to the ruler. And the critical height, which are the critical conditions that might, which are the things that we want to be analyzing in this phenomenon, and also the deviations that might be caused in her experiments. Okay, that's right.
Yes, so please start the discussion.
Okay, so as you mentioned in your report, you said that atmospheric pressure balances the gravitational force of the ball acting on the ruler. So does air flow in the space under the paper upon colliding?
Yeah, it does flow, but it won't flow too much because the ruler only go up and only the middle. So there's no good turnover.
So you think that there is no air flowing in the paper?
They are small enough to be.
Okay. Can you please come to the blackboard?
Yeah.
So I can talk about the atmospheric pressure. So suppose this is the paper, and then you put a ruler right here, right? And so how do you think that the atmospheric pressure has an effect on the ruler? So suppose that the ball is from here and down to the ruler. So how does the air pressure do the force of this? Okay, so this is the ball on the top, right? So, but what if I change the ball releasing height? So just gently putting on the ruler. What do you think will happen?
What do you mean?
Just
You
like,
it will fall up or not?
yeah.
But you have to see the length of this and also the area. So these factors involved.
Okay, if it was the last situation, like you put it right here and you drop it, but it doesn't fall off. But if you put the ball gently on the ruler, what do you think will happen?
It won't fall up.
It won't fall off?
Yeah.
Well, since that the air pressure is generated by the pressure difference in during this phenomenon. So as the ruler is being impacted, the paper will become like it will get lifted up, right? So it will cause the pressure difference, which is because the volume of the volume under the paper will be a lot larger, which causes this pressure to increase, and which will then generate the force. And also, you didn't consider that there might be some of the Bernoulli's principle that is happening in this phenomenon, because as the volume of the air, the volume under the paper increase, the smaller pressure allows air to flow in, and as the air has a more velocity, it will cause a force of another force coming down. So you can explain that if you put a ball, even though its force is smaller than if the ball is on the top, then if you put it gently, the paper will fall along with the ruler. You agree with this? Alright.
Do you have any experiment about this?
So let me demonstrate. So let's see this. Okay, so see it bounces itself, right? But however, you gently put it up,
No,
it flows.
you mean gently put it?
Yeah,
I thought you were talking about it's actually just putting up.
Yeah,
Oh,
it flows.
okay.
So this is so as I mentioned, it's because of the pressure that is the pressure difference that is generated from the pressure difference that is generated by the increased volume under the paper. So do you agree with me?
Yeah, that would be my improvement.
Okay, thank you. How do you think that different materials of the ruler would affect the phenomenon?
The deflection.
Okay, so can you?
Explain about
Okay, yeah. I want to change to the page where we talk about the deflection.
it didn't show in my presentation because there's something wrong. So,
Okay.
So
Can you briefly explain what is the deflection of the ruler?
Yeah. So here, this is the deflection. And so F is the applied force, and L is the length of our ruler. And E stands for the modulus of elasticity of the material. So in different materials, they have different E. And the I stands for the moment of inertia of the ruler. And so you can see that the external force influence and also the length of the ruler and also their material.
Okay. So what can you gather from this which you call the deflection of ruler? What information can you gather from the deflection of ruler?
So you can see that when the deflection of the ruler is bigger, then it won't fall up that easily because it will deform rather than just falling up.
Okay. Since you have mentioned that elasticity is also in the deflection of the ruler, can you explain how elasticity will affect the phenomenon?
But in different materials, there are different elasticity.
Yeah,
so
I mean, how does different elasticity of the ruler? Like, if one ruler is more elastic, how would the phenomenon change?
So when the elasticity is bigger, then the deflection will goes back, and so the ruler won't deform that easily. So it will fall out more easily.
So you think that if it has more elasticity, the ruler will fall off more easily, or it will not fall?
I think it will fall out more easily. I think it will, yeah, fall out more easily.
Well, I think that if the elasticity of the ruler is bigger, then the ball will bounce off. However, how the critical height is affected by the protrusion of the ruler. So how can you come to the fact for again? So how do you think that the point of the ball drop, the position of the ball drop? So if it's A inverse and the ball falls in A to point B or point C, how do you think it will affect the phenomenon?
Oh, so when the ball is closer to A, then it is more closer to fulcrum. So the length of the arm of the force is smaller. So the torque of the ball is smaller. Then it won't fall off that easily.
Okay, the opponent agrees with the report. So, can you explain why the crumpled paper has not a significant phenomenon? Like, why did the silicon height?
It's because when you crumple the paper, then there's then the paper there's no I mean when the paper is crumpled, then the area of it is smaller, and also because it's crumpled, so there are many tunnels for air to go down to the under the paper, so the atmospheric pressure won't be influenced that much.
Okay. Did you obtain the contact time between the ball and the ruler? Did you measure the time between the ball and the ruler intact?
Yeah.
So, what means that the ball will fall on the ruler, right?
Yeah.
So,
I know what you mean.
okay, and how do you think it will affect the phenomenon?
Can I show you?
Yeah, sure. Oh, well, can you just briefly explain?
Oh, yeah.
Okay.
Here, so the torque of the ball equals to the arm force of it, and times the delta p, which stands for the velocity. It's the
So if the contact time is bigger, will the critical height increase?
when the contact time is bigger, then the torque of the ball is smaller. Then so the ruler won't fall out.
Okay, thank you.
that easily.
Okay, so this is my summarization of the discussion. So firstly, pressure difference is the main reason that the ruler remains on the table. However, if the object is gently put on the ruler will fall because of it's not really all of them are the atmospheric pressure. And also, if you use high elasticity ruler, the ball will easily bounce too, and therefore the critical height will be higher. And thirdly, measuring the force acting on a ruler is calculated by the ball mass. The contact time of the ball didn't have significant effect. And cruel height will increase when the length increases. And also, if you drop the ball closer to the table, it will cause the torque of the ruler to be small. Okay, thank you.
Okay, questions from the reviewer.
To the reporter, I would like to ask you, do you think that a torque due to the pressure is the same throughout the process, like the whole phenomenon?
Can you say your question again?
Do you think the torque caused by the pressure will be the same throughout the process?
Yeah, if I do it in the same condition.
Then do you think that the use of the angular momentum or the rotational energy explanation will be suitable for this problem?
Yeah, I think it would be so.
Okay, thank you. Do you, like for both opponent and reporter, do you consider friction between the paper and the ruler and the table as a relevant parameters? Like the friction between the materials you use in the experiment?
Yeah, I think they are small enough to be known.
Well, however, I think that the friction between the paper and the ruler will have significant effect because the ruler and the paper, if they have more friction, then it will cause the paper to silo.
Yeah, thank you. So do you think the arm of force is the main factor, or it is because of the horizontal direction will just provide more area for the airflow, according to your experiment about the vertical and horizontal papers?
I think it is mainly influenced by the unfold object.
Okay, thank you. So, do you think the pressure, like to the reporter, do you think the pressure difference will caused by the increase of volume or the Bernoulli principle? Because like we believe that Bernoulli principle doesn't actually play a significant role in this condition.
Oh, I didn't do that in my experiment, so that is not my main focus.
What do you think?
Can you explain that?
So do you think the pressure difference will cause the increase of the volume, or it's because of the Bernoulli principle that you just mentioned when you were at the lab?
Well, it's the pressure, the volume would increase, and then the Bernoulli's principle would act.
Okay, so regarding your experiment setup, we want to ask you like how do you maintain the ruler to be straight stated on the below the paper, since we believe that if the ruler is somehow tilted or not straight, the result will be different.
When there's a need, we will change the ruler immediately.
Okay, thank you. and fellow debaters. This is Team E1 report reviewing problem for Team E1. So below is a problem statement, and the reporter teams are focusing on the relevant parameters and also angular acceleration. So to summarize the report, they explain the phenomena is by placing a paper on a ruler as a bowl, and the bowl falls, the ruler will just remain on the table. And they use the air pressure, torque, and parallel axis theorem to explain this phenomenon. And the experiments, they first do a preliminary experiment about using flattened and crumpled paper to choose which kind of the paper they would use. And they include parameters including type of ruler, type of coverings, direction of paper, area coverage, and also the height of the ball dropping. Which, as the ruler is more flexible, they will resist more force, and the folders will actually better receive the force even though the weight might be a bit different. And also, since the vertical arm of force will actually increase, and as the paper's area increase, there will more force be resisted. So there's some advantages that the reporter has in her presentation, including that it does a really detailed experiment, and also they include multiple parameters in their experiment, and they also take certain boundary condition into their condition. Also, however, there are lack of connection between the theoretical data and experimental data, and also they didn't actually elaborate on the angular acceleration and velocity as they mentioned as their focus. And also there are lack of quantitative results. And regarding the opponent's presentation and discussion, we agree that they got a really good acknowledgement on airflow affecting this phenomenon, and they do got a lot of their own perspective on their airflow and relevant factors. And also they did a really good demonstration on the sliding condition and the method. However, they have somehow lack of consideration on the different angle of the forces, and they got a bit vague when they are explaining the different materials influence. So they first discussed about the airflow entering as the ball hit the ruler, and the opponent also asked about how does the atmospheric pressure acts on ball. So the opponent also used as a ball put on the ruler to explain this phenomenon. And reporters think that if the atmospheric pressure is small enough to be ignored, and also they agree on the opponent's choice that the ball will fall as it goes. So we as a reviewer agree that airflow will actually balance off the air pressure, which actually definitely plays a role in this phenomenon. So regarding next is about the opponents asked about the different materials that use in it. And the reporter shows the formula they use to calculate it. And we believe that elasticity of ruler will definitely affect the phenomenon. And next one is about next one. Next one. So about the position, which the reporter thinks that as the arm of force will be smaller, the torque will be smaller, and we believe that it will be the same as the reporter. So next. So they explain why crumpled paper will be less effective, and the reporter answer will be there will be less contact surface. Thank you.
Thank you. The concluding remarks.
So this would be our summary. So the opponent asked me how do my experiment data and theory match, and I said they match. And so he asked me whether the area of the paper or the length of the paper influence our experiment. I think the area is more important. And he asked if there will be a limit about our critical height or other conditions. And I said there will be a boundary, but when we check other conditions, and the boundary also change. And he also asked me how deflection affect our experimental result. And I said when the deflection increase
and the ruler won't follow that easily. And here's what we can do in our future research and our improvement. So we can maybe calculate the result to make the experiment and the theory have more connection and more persuasive. And also, he also provides me some suggestion about when the volume of the air under the paper increase, then the pressure would get much more force, and that is a good suggestion. Thanks.
Thank you. Thank you for your discussions.
Remember seeing you show some formula on page 14. Is this your model prediction? Is this your model prediction? Yeah. Did you compare this with measurement?
You mean the result that we measure the temperature?
Did you do that? Did you compare this prediction with your measurement?
But we can't measure.
No, just yes or no.
No.
Do you think the elasticity of the ruler crucial reason for the phenomena? Is crucial for the phenomena. The elasticity of the ruler for the phenomena.
Yes.
Yes.
It is most important reason for the phenomena, the elasticity of the ruler.
It's not the most important, but it's one of
It's one of the reasons, but it's
Not
the
the
most
main.
important reason.
Not the main one.
It is just like relevant parameters, but it won't actually affect that much as accurate resistance.
Yeah, I agree.
Okay, the opponent just did an interesting demonstration of dropping the ball. So the lower dropping height actually helps the flipping of the ruler. So what's your take on this? Because we expect higher dropping height would help, but in that case it's the opposite. So I'm interested in what's your opinions on this. Maybe let me start from
First, okay, so well, the reason that the ruler fell is because the objects stayed for a period of time on the ruler, and therefore the pressure difference that is that is generated in a short time. After a while, after the air flows in, then there is no pressure difference, and therefore the only force acting on the ruler is the weight of the ball.
I also agree with the opponent, but I also think that when the height of the ball is higher, then the velocity is bigger, so the torque will be bigger, and that also influences our results.
So we think that the contact time was also affected. So if you drop the ball like with a lower height, the contact time will increase, which will also cause the pressure difference to be more quickly balanced, and it will cause the ruler to fall.
Okay. 5, 4, 5, 6, 4. Scores for the bottom. 7, 7, 5, 6, 5. Finally, the scores for the Euro. 6, 5, 6, 6, 6. Okay, thank you very much. And let's take a final break.
请问一下，那个点心是在哪里？
在我不用讲。
不是，其实我要查包。
你要查包？要去回去理学院的那个。
这么远？
对。
我不知道这里有没有。
这里我不知道。
去年有，那今年不知道有没有。
我不确定，
来问一下机动，还有对讲机。
就是。啊？这边5楼。哦，5楼哦，好，谢谢你。
再按一点点。
我只是写你是没有说什么。我待会请人，他们人多一点。不止没有 theory， 连 theory 都没有。
不
这样子可以完成的是，那你是感觉像基地是。
老师是可以来看的。
可以啊，张老师有申请就可以，需要带那个证。
Problem 4, shooting rubber band.
So we accept the challenge.
So you will take this. You take. It's 4 rubber band. please start your presentation.
Honorable juries and fellow competitors, I'm the reporter from Team Excelsior, and I'm going to report problem number 4, shooting rubber band. So here is the problem statement. A rubber band may fly a longer distance if it is non-uniformly stretched when shot, giving it a spin. Optimize the distance that a rubber band with spin can reach. And I'll be mainly focusing on why do rubber bands fly farther with spin, and also the parameters that affect rubber band's flight distance. So this is my outline for the report. So I will first be talking about my preliminary experiments, and then go on to my theory, my experiments of different parameters, and finally my conclusion. So preliminary experiment. I'll be talking about phenomenon demonstration, my setup, and my qualitative explanation. And so here's the phenomenon demonstration. So this is the demonstration of the rubber band shot without spin. And as you can see, the rubber band's form is very irregular during its flight. And here is the observation of the rubber band shot with spin. So here you see that the rubber band is shot with spin and it flies faster. And this is my setup of the experiment. So we use aluminum extrusions to support the launcher, and then we position the launcher to be exactly 1 meter above the ground. Here is the closer look at our launcher, and so the thing on the right, it allows us to change the angle of the launcher, and then for the launcher, it's on its front, the supporter falls down during launch, so it won't affect the rubber band's trajectory. And here is my qualitative explanation. So at first, the rubber band is stretched and shot, and then the rubber band will shake irregularly after it is launched into the air. And then, after a short period of time, the rubber band lands. And here's what it looks like when the rubber band is in the air. So it only launches with its stretch potential energy. And during its flight, it's easily affected by air resistance and turbulence due to its irregular shape. And this is when the rubber band is non-uniformly stretched. So when the rubber band is non-uniformly stretched, the two sides of the rubber band will have different elastic force. So if you stretch this side, it will have a bigger elastic force. And also note that the potential energy will also be larger because of the non-uniformly stretch. So this is how the launch with spin is in the air. So when shot, the rubber band becomes a long, thin form because of the different elastic force. And then during its flight, the rubber band starts to spin. And after a short while, its energy decreases. And then finally, the rotation velocity of the rubber band decreases. And then it goes back to its original form. And here's how the ejection happens. So first, the rubber band is non-uniformly stretched when shot and giving it a spin. Although that because of the spin, the rubber band stays in a ring shape during its flight. And the rubber band will land at a far distance because it is more stable, and also it has a slightly lower air resistance because of its ring form, which allows it to achieve farther launch distance. So, and then here's another effect that might affect the phenomenon. So it's called the Magnus effect. So when the rubber band spins, the Magnus effect happens. And what it does is that it generates a force dragging the rubber band sideways, which will change its trajectory. So as you can see, it will change its trajectory. And here's the theory. And to calculate the ejection velocity, so this is the force acting on the rubber band, the force that the rubber band has according to its elongation. So this is the equation, and then we can then integral the force of the length of the rubber band to get our the potential energy stored in the rubber band. And then as we get the potential energy, we can calculate the velocity, the initial velocity of the rubber band when it's shot. And for the launch distance, we have to consider air resistance because it's a very important factor, and because of the rubber band's small mass. And then for this is the equation for the drag, and then we let B as the constant in front of the V squared, so we can easily calculate it. And so we integral the time, and then we can get this equation, so we can calculate the launch distance. And here's the theory for the non-uniformly stretched. So first, we have to non-uniformly stretch it, and as you can see here, we let y as this thing, so we can easily calculate it in our theory. So this is the potential energy stored in the rubber band, and after that, we can calculate the velocity as like the procedure before, and then we can integrate it into the distance of the rubber band. And also the initial angle of launch. And we can get the flight distance by numerical solution. So firstly, we have to define the initial positions of the coordinates. And then we have to calculate the initial velocities. And then after the velocities, we can use the force to get its the relation with the air resistance, and then finally we can get its distance. So this is my experiment. So this is the ejection stretch length. So we vary the stretch length to do this experiment, and then as mentioned before, the velocity is dependent on the stretch of the rubber band. So the whole ejection stretch length will cause the distance to increase. So here, if the x decreases, then the distance won't be as much. And here is the non-uniformly stretched length. So as mentioned before, this is the theory, and then we can know that when stretch length increase, the slope will become smaller due to the smaller y, and also the air resistance. And when L increase, the distance increase due to larger potential energy. So as you can see here, the one with bigger deflection length, it will have more larger distance. And also, we can know that when a rubber band is unevenly stretched, it will cause the rubber band to spin, right? So the spinning motion allows the rubber band to become more stable and therefore lower air resistance. And thus, the non-uniformly stretched gives the rubber band a faster velocity, and therefore landing distance increases. And then here's our experiment on the experimental data of how we vary the initial ejection angle of rubber band. So for 0 degrees to 30 degrees, when the angle increase, the distance will be longer because due to the longer time of flight. And also we got this from the numerical solutions, and it gives this longer flight distance. But as for the 30 degrees to 45 degrees, because when the theta increase, the velocity decrease, and it will the velocity of the x-axis, which is horizontal to the ground, will decrease, and therefore it will decay due to the air resistance, and therefore having shorter flight distance. And also, we can know that the contact area will be different with various ejection angle because of the rubber band's angle with the horizontal line. And with deflection length is also an important factor. And considering different air resistance, we can optimize the farthest distance that the rubber band spin can reach. So my conclusion of the report. And why do rubber bands fly farther than spin? So first, the rubber band will have lower resistance, and it will have increased flying velocity. Also, I have to add that the potential energy of the rubber band will be increased if you non-uniformly stretch it. And then how I optimize the distance is by using it to optimizing the angle and also the stretching the deflection length to a perfect value. So as you can see here, the furthest distance we have reached is the elongation of 30 cm and the deflection of 6 cm and also the initial launch angle of 30 degrees. But elongation will play a very big part in this phenomenon. So with longer elongation, it will cause the rubber band to fly farther. Okay, thank you.
Thank you.
So there are a few questions I would like to ask the reporter. First, I would like to ask about the elastic limits that the rubber band can reach. Do you consider that as a parameter? So since in order to provide a maximum optimization of distance, I think you should consider boundary conditions. So did you?
Okay, so I tested the boundary conditions of the rubber band. So to our rubber band, it will reach the its elastic fatigue point.
Okay. So which one do you think is the main factor that affects cause a longer distance of the unevenly swept rubber band? Is it the air resistance or the increase of potential energy?
Well, as I mentioned in the report, it will be the elongation will cause the potential energy to be bigger. So potential energy.
Okay. So I also wanted to ask that why do you think this unevenly stretched rubber band can have less air resistance?
Well, because of its more ring shape and its more stable shape.
Okay. So do you think that if you apply the Hooke's law in the rubber band, do you think this K value will fluctuate throughout the stretching length of the rubber band?
As I mentioned in my theory, so because of the rubber band's material, so the rubber band won't fit Hooke's law.
Okay, so you mentioned the Magnus effect. Have you considered shooting it in different direction? Since you mentioned that it can cause trajectory, but if you shoot it in a vertical way, this trajectory can be transferred into a lift. So have you considered that?
Yes, I have considered that, but we didn't do it.
Okay. Right. honorable judges and worthy opponents, this is Team B1 opposing shooting rubber band. So the problem statement is about rubber band can fly a longer distance if it's uniformly stretched. And the reporter focused on why rubber band fly farther with a spin, and also the relevant parameters that might affect the flight distance. So for the phenomena, the irregular when the flight without the rubber band will fly irregularly without a spin, and the spin will make the motion more stable, and it will fly faster with spin due to different elastic force with stretch, and it's also affected by air resistance and Magnus effect that causes the trajectory. So for the theory part, the reporter calculates the potential energy stored and calculates the distance, and also consider the initial angle by position, velocity, and solving the differential equation considering the air resistance. And for the experiment, they first test the ejection stretch or the elongation, that the uniform stretch increase the flight distance, and also the non-uniform stretch, once the length increase, change the distance will diminish, and it will be more stable, therefore that's air resistance. So for the ejection angle, they found out that the 0 degrees to 30 degrees, as the angle increased, there will be a positive correlation. However, after 45 degrees, there will be a negative correlation. So next, I would like to talk about the pros and cons. So the reporter said the stable rubber band projector, and they have a clear qualitative explanation of the phenomenon, and they also have a clear graph for the experiment data. But however, a lack of data to connect with the Magnus effect, and also lack of quantitative explanation, and also not having deep consideration for non-uniform condition. And they have lack of explanation of air resistance practical effects. So here are some discussion points I would like to discuss about in the next section. First is the stable motion of the rubber band. So I believe that there's some way that the reporter can actually describe this unstable motion, its effects to the distance. And also, for the theory part, I would like to talk more about this boundary condition, that since this question is about optimizing the distance of the rubber band. Therefore, once the rubber band exceeds the limits of elasticity, it will not be able to fly longer. And for the air resistant part, I believe that the reporter provides a qualitative analysis about this air resistance towards a spinning rubber band. However, they didn't use the theory to validate this effect, so I would like to talk about that. And also, they mentioned that the rubber band will spin. However, I think there's some way that we can actually calculate this angular momentum during the motion. So, for our discussion point, I believe that when we're optimizing this shooting rubber band, I believe that the torsion can actually increase this optimization of distance. And also, the temperature can affect the Young's modulus of the material of the rubber band. Therefore, it might be also a relevant parameters, and also about the direction of Magnus effect that I just mentioned in the last discussion point. So now, I would like to invite the reporter on the stage. So, why do you think that this unevenly stretched rubber band can provide some more stable motion?
Well, because of its rotational inertia, so it won't be easily affected by other forces such as air resistance.
So can I use the blackboard? So, in my perspective, I actually connected to the angular momentum I just mentioned, that if we consider a rubber band as spinning, I believe that this angular momentum that the rubber band possesses can decrease this precession motion of vibration, because this, like you just mentioned, I believe this unstable motion is due to this vibration, and this vibration can cause a loss of energy. So if the angular momentum, if the rubber band possesses angular momentum, it can decrease the effects of the precession motion. So what do you think about that?
Yeah. So because of its spin, you will have more rotational inertia, and then therefore it will be more stable. Or do you mean that when the rubber band, if it's not non-uniformly stretched, if it's uniformly stretched, it will cause a kind of like a buckling motion? Do you mean that?
Not really. I'm trying to elaborate on your theory that, because I agree with you that you said if it's spinning, it will start. It will have a more stable motion, therefore provide some longer distance. I totally agree with that.
Yeah.
So I'm trying to elaborate on that, and I believe that this is related to angular momentum. So do you agree with that?
Yes.
So since it's agreed with the angular momentum, I think it's necessary for to calculate the angular momentum so that we can actually quantify this spinning effects on this decrease of unstable motion. Am I correct?
Well, there must be the stable motion. It has an effect. However, if you non-uniformly stretch it to a degree, it will cause it to be a little bit more unstable because of its non-uniformly stretch. Its force between the two sides would be too irregular that will cause it to fall.
So are you trying to say that if it's unevenly stretched to a certain degree, it will be like a peak?
Yeah.
Okay. So, but what I thought about that is actually because I think the whole process, the main reason the rubber band can shoot longer distance because of the potential energy. So, so I still believe that if you unevenly stretch a longer distance, it can fly longer. Because I think this vibration motion is not as significant as the potential energy.
Yeah. So as you see, if you non-uniformly stretch it will actually have a larger potential energy.
Okay. So next, I would like to discuss about this boundary condition. Because do you agree that there are two ways of increasing this distance? The first way is the initial stretch of the rubber band.
Yeah.
So, and the second way is the
non-uniform stretch.
Exactly. So, I believe that if once it's unevenly stretched, it will provide a thicker string and a thinner string.
Yeah.
So, the boundary condition I would like to discuss is about this thinner string, because I believe that the rubber band once elongated to a certain length, it will actually exceed its elasticity limits. So, let's say if this elasticity limit will be like x, and the stretch of the original stretch of this rubber band will be a. And the unevenly stretched length will be like b. So in order to not let this thinner string to exceed this elasticity limit, a plus b must be smaller to this x.
Wait, I thought x was
no, x is the elasticity limits that the rubber band can reach.
Yeah.
So, I mean, this problem is telling us to optimize this distance. So, since we both agree that this a distance stretching length and this unevenly stretched length can increase the distance of the rubber band, I believe that it's necessary for you to consider this relationship between this equation, that you need to find fast stretching length and elongation length, that there will be a certain value of A and B that combines that it's exceed this elasticity limits will be the optimization of this rubber band. Do you agree with that?
Well, as I mentioned before in the discussion, if the two sides of the elongation force is if one of them is too big, then it will cause the release to be unstable. So, yeah, it's.
Do you agree with that?
Yeah, I mean, it's very great to calculate it.
Yeah, so I think you provide an optimization of distance, which is great, but I believe that if we conduct more detailed calculation of this condition, you can reach a more reasonable and a solution with more reliability. So I would like to talk about the next topic. So have you considered that, because when you're doing the experiment, it's really easy when you're stretching the rubber band, it will cause a torsion, which means that if you spin this one in this way, the rubber band will be like a bit like this.
What do you mean that you?
Yeah, exactly. So what do you think this torsion will have its effects on the distance?
Well, in our experiments, sometimes the deviations are caused by these torsions because it will cause the rubber band to not be released stably, and then therefore decreasing its potential distance. So I think that the torsion would cause the release to be unstable.
It's a really fair explanation of this torsion effect. However, I do believe that once there's a torsion possessed in the rubber band, this restoration force will increase. So therefore stretch to a longer distance. So I think torsion should be a part of variables that we can investigate in the future research. And I would like to discuss about the Magnus effect. Yeah, like I just mentioned, that if it's launched vertically, that because you said if it's launched horizontally, it will be a trajectory. So, which when you transfer it into a vertical situation, this trajectory deviation can be a lift that causes this rubber band to be able to fly longer. Am I correct?
Yes.
So, I believe that in order to optimize this distance of shooting rubber band, this can be a part of future research. Am I correct?
I can believe that.
Okay. So, next, I would like to discuss about the temperature. I think temperature can increase the Young's modulus of the rubber band. Therefore, it creates a more elastic potential energy when stretching. Although it's not a really significant effects of this temperature of the rubber band, I do believe that this temperature can be considered in this experiment because I believe the elasticity limits or the boundary condition that I just mentioned can also be fluctuated through the deviation of the temperature.
Well, if the temperature increases, it will cause the rubber band to be a little bit softer, and then it will have a slightly lower elastic, smaller elastic. But however, can I please, can you briefly explain what is Young's modulus?
So Young's modulus describes how the material will, in this case, elongate throughout the stresses.
Yeah.
Yeah. So that's Young's modulus. So based on your the explanation you just said, you said that the increase of temperature will soften the rubber band, therefore cause the rubber band to have a less distance. So I believe that if you do it in another way by make the temperature lower, you can create a longer distance.
Yeah, thank you.
Thank you. Mrs. Marcus, go ahead.
Okay. Please summarize.
To summarize the discussion, at first we discussed about the vibration motion to this rubber band. That we both conclude that the angular momentum provided by the unevenly stretch can decrease the precession motion, therefore decrease the loss of energy due to this unstable motion. And then we then discussed about the boundary condition that there should be a maximum value that we choose to elongate the rubber band initial length and even stretch it. There will be a maximum height, and that's the part that maybe should be considered when we are trying to optimize the distance of the shooting rubber band. And also, we consider the torsion that So the torsion can, I believe the torsion can increase this elasticity of the restoration force of the rubber band, and the opponent believe that the torsion will makes the rubber band more unstable, therefore cause the loss of energy.
Okay,
Thank you.
thank you. Questions from?
Please switch to the setup page. How do you use this setup to make the rubber band uniform, non-uniform exchange?
Well, you just stretch it and then you fix it at the two sides, the launcher.
How to make it non-uniform?
Well, you just stretch one of the sides more and then fix it on the launcher.
So you use by hand or something?
We use our hand because it's not really costing any work.
Do you think we use hand to do this experiment is a good way or?
I think the use of hands won't create a large deviation in this experiment.
Okay, thank you. And did you consider the energy loss in your experiment?
The energy loss in my experiment, well, yes, we consider the air resistance.
I think you mentioned a really good point that if we observe the damping motion of the rubber band, you can see that there will be a heat loss during the stretching of rubber band. So, yes.
And please switch to the page that has the chart. I want to ask, this is an error bar. So how much percent do you use in the error bar?
What do you mean? What do you mean by how much percent?
So how can you draw the error bar?
Oh, it's the standard deviation.
And to the problem statement page. You say that did you have the longest distance that a rubber band with spring can reach?
Yes. According to our experiments, it should be 30 degrees and 6. However, it could be longer, but it's the experiment that we have conducted.
So what's the data? Can you show me the data?
Here.
So the 30 centimeter is the longest.
Yeah.
Time is up.
we can understand very easy. And his explanation is very complete, and he has enough time. But he didn't have enough observation of the experiment. And the opponent, he considered about the angular momentum and the boundary condition. That is a very good opinion of him. And he has a good explanation, but he didn't consider energy loss. And while discussion, the opponents asked, will different direction affect the experiment? And the reporters say that he considered about that, but they didn't do the experiment. And to the opponent, he asked, the main factor affect the experiment. He said it's a potential energy. And while discussion, the opponent asked why spinning rubber band is more stable. And the reporters say spinning rubber band have bigger moment of image. And I agree with it. And the opponent asked how torsion affects the result. And the reporter said that the torsion caused rubber band to be unstable. And I asked them that, is there any energy loss? And they both say yes, there will be energy loss. And about the setup, he used hand, but he said that it won't cause big influence. And the opponent agreed with the reporter. But in my opinion, I think it will cause a little bit influence. And my suggestion to the reporter is that they should do the experiment by changing distance, but not a tilting angle. Because I think the angle won't affect the range of the rubber band can reach. But the distance is the main point that the rubber band can reach.
Thank you. Concluding remarks from the reporter.
Here are my concluding remarks. So firstly, the elastic limit has been considered in our experiment. And also, the elongation is the main factor of how long the distance the rubber band can reach. And then, and non-uniformly stretched can make the shape more stable. And then the material of the rubber band doesn't fit the Hooke's law. And then if you stretch the rubber band in a vertical way and shoot it, it will generate a lift. And however, the Magnus effect is not the main factor which would cause the distance to decrease. And we have enough observation from the experiment, which we have shown in the beginning. And then the larger potential energy is caused by the uniformly stretched when the main reason of the phenomenon. And then the deviations might be caused by torsion. And then if the temperature is lower, the elastic force would be bigger. Also, I would like to add that not just by changing the angle, we solely do our we do our experiment very importantly on how long the elongation is. But however, you cannot change the distance according to the reviewer's report. Okay, that's my concluding remarks. Thank you.
Thank you very much. Questions from students?
Can you show page 15? 15, no, sorry, 18. No, where's the force or previous one?
earlier.
Oh, you mean this
model?
this force?
Right.
Oh, this force we have reference from a theoretical.
The model.
Yeah, this is model from a reference, which is it's a little bit.
What is the model?
What is the model?
Right.
Well, the model is that the force is equal to 2 multiplied by alpha and the elongation.
So do you think that the spin is not the most important result for the reason for the result?
Well, for the distance, the elongation is the most important. However, if you add a spin to it, it would increase the distance more.
Little bit or
like a lot. However, but the elongation is still more important.
Okay, so how do you think? The spin is the spin the most important reason for the result?
I think the spin is the most important.
Why?
Because the spin can make the rubber band more stable. And it can fly harder.
I think the potential energy is the main factor because the unevenly strapped rubber band can create a lot more potential energy, and the spinning can reduce the air resistance. However, the surface area of the rubber band is actually pretty small, so I believe the spinning is actually a minor factor in order to optimize the distance.
I'm curious about that force. How come there is alpha?
Oh, the alpha is a constant for the rubber band. If you stretch it, the alpha will be the same for the force. We can calculate the alpha by stretching.
There is 10 digits.
Oh, it's measured. Like we have the elongation, right? And then if we have the right half, and then we divide it by the force, and we can get the alpha.
The different rubber bands give you different coefficient.
Yes. And so we, when we are doing the experiments, we have to find the rubber bands that would have the same force stretching to the same elongation. Which means that the rubber band, we have to find the rubber bands that will have the same elastic force.
This constant is only for one particular.
Yes, for our rubber band. The constant must be measured if you're doing the experiments on different rubber bands.
Just, do you think it's necessary to write so many digits?
Well, it's not, but we just showed it.
Scores for the order are 6, 7, 5, 7, 6. 6. Finally, the scores for the viewer are 5, 4, 4, 5, 4. Okay, thank you very much for participating in this event. Good night.